Hello, I'm Jose Tellado, and I lead technology at NetInsight. And this.
Yeah, I'm Rajesh Bhagwat. I'm responsible for engineering for NetInsight product.
Okay, so we're going to give you a little bit overview of NetInsight. This is a dedicated team of a collection of Wi-Fi experts and data science experts. And in addition, we obviously leverage all the Wi-Fi experience that sits in Aruba to build these insights. So just for those of you that may not know what NetInsight looks like, this is just a high-level architecture diagram of how it works. It's a cloud-based platform. And right now, we have under management close to 200,000 access points. And right now, the user consumes it as a dashboard of insights, root causes, and recommendations. Of course, we want to close the loop and make this a self-driving network, but that's in the pipeline. So what about data sources? And of course, your insights are only as good as your data. So the data has to be high quality and high quantity. So on the quality side, we get most of our data from access points, controllers, Airwave, mostly for database type stuff, ClearPass, and DHCP servers. Rajesh will spend some time in talking about some of the insights we get from ClearPass and DHCP servers. I will spend a little more time talking about the insights we get from the RF Wi-Fi domain, which is mostly from access points experiencing station problems and combinations of radios and controller information. So as I mentioned, we have close to 200,000 APs under management. These are some of our, actually these are paying customers. We have in the pipeline another 15 POCs. Our typical customer has between 3,000 and 15,000 APs, but we have some that only have 500. And they benefit from the other 200,000. So if you only have 500 APs, you're not going to learn a lot from your 500 APs, but you can learn from the other 199,000 in the database. So NetInsight has a lot of machine learning engines running on it. And sometimes you have a connectivity event that you think that a rule will take care of it. But this machine learning algorithm feeding it some contextual information to make sure the connectivity event is more contextual, more significant. But in any case, this is our train of machine learning algorithms. We are currently sitting on the left. We're working on the middle and the right side. What's happening on the left? So clearly, you have to make sure the data is accurate, clean, and voluminous. So a lot of what we've been doing early on is machine learning algorithms that are a little more intuitive, more robust, that actually give you us outputs, things like feature importance. So you could actually see if you're building a model that's learning some strange behavior that's not real. So most of what we're using right now are regressors, classifiers, clustering, and anomaly detectors. And what can we achieve with these right now is we could optimize radio frequency parameters, and we're currently optimizing about 10 to 15 parameters. We could help with root causing connectivity problems, and we could also provide outdoor AP planning. And I'll spend some time in a couple of these. Where we're going very shortly, I mentioned there AOS 8.4 and 8.5. These are the next releases of 8X, months away. So we're going towards now our end customer gets insights or visibility as a dashboard and a card with some steps he has to follow to actually fix the problem. So in the next versions of iOS over the next few months, we'll actually be pushing back some of these config recommendations and some of these RF parameter optimizations so that nobody actually has to touch anything to fix the problem. Another feature we're building in for the next couple of releases is this green AP, which we showed in ATM. And basically what it does is when you deploy APs, you deploy them for the worst case scenarios with the highest capacity. But in practice, many APs are not fully loaded. And based on station models versus time and space, you could actually power down some of your RF AP capabilities and save power. But what's in the pipeline? So we obviously are working on deep learning algorithms. None of them is in production. The stuff they show on the left is in production. Those 200,000 APs under management are doing those machine learning algorithms right now. The stuff here on the right is mostly on the side, trying to figure out the models, make sure the data is correct. But in the pipeline, we have enhanced AP modes, where we have enhanced telemetry, where we could actually contextualize that telemetry resolution, for example. The telemetry will be better calibrated, in part because we built these simpler machine learning models early on that found problems with telemetry. Since we control all the sources of telemetry, we could also fix if we find a problem in telemetry and just make everything better. Another thing we could do once we do the middle step of self-driving is if we have a solution that's good based on peers, but we think there's actually better solutions, we should actually optimize in the neighborhood of a good solution and use reinforcement techniques to actually find a solution that nobody's ever tried because they weren't brave enough to try it, but we could find a solution nobody has ever done and we haven't seen in our 200,000 AP database. So these are the 4 big categories we're going to explain that machine learning is helping us solve. So the first is RF config optimizations, and it's the bulk of the presentation. There's some RF performance related, and then Rajesh will talk about device analytics and connectivity issues that we found. So radio frequency configurations. So this is actually a big part of our offering. What ends up happening is most of our customers have somewhere between 1,000 and 15,000 APs. And they have somewhere between 100 and 300 buildings. So you have a couple of choices. One is use the default Aruba configs. Pretty good. But when you're dealing with auditoriums, libraries, classrooms, and outdoor APs, the default configs are not that great for all these environments. They're kind of a robust solution, kind of somewhere in the middle, but they're not optimized for any of them. Our really brave customers, they'll have like 2 configs. One for like residence style, and the other stuff for like high density. And maybe the outdoor APs are maxed out. And the really advanced may have 4 or 5 profiles, but it becomes out of control. So, and the reason they don't do this is too many combinations, too many things to try. They don't have enough data to figure out if it helped or hurt. So what we do right now is we profile the Wi-Fi environment, we look at all the peers, we learn from peers, and suggest recommendations based on what peers have tried in that environment. And the current form is consumed. This, by the way, these are screenshots from our dashboard. To speed up the presentation, we're not going to use a live demo, but you could click somewhere and get this card. And this is a card that shows for a specific building, how does this building compare against peers with similar environments. And these are the RF config knobs that are being suggested versus the ones that are currently implemented. And to get an idea, we've probably have a few thousand buildings under management on those close to 200,000 APs. We've recommended at least 100 of these. And there's some pretty really bad setups out there too. So this is actually how the RF configuration engine works. So the top part shows the model building phase. So basically, parameters, model, desired outputs. What things do we use to actually characterize the environment? So there's Wi-Fi infrastructure features, like what AOS flavor you're running, because the RM algorithm changes versus time. So a different AOS version may have a different behavior in your building. The AP model, of course, a 2x211n doesn't behave the same as a 8x8AX. And some people actually, you could tell they chose the configs 4 or 5 years ago for an 11n AP, and they upgraded 2 or 3 times along the way, and they're not brave enough to change the configs for the 4x4s, and they still have 2x2 type configs in there. Other things we use are the path loss between APs. Most RM algorithms actually use this path loss as the main feature to figure out what channels and powers to use. Then things like cross-flow propagation, how far the APs. I mean, these are Wi-Fi infrastructure. We obviously have many more, but these are just key examples that people remember. But then there's the Wi-Fi client features. This is actually very important, because setting up your APs based on how they APs seeing each other doesn't tell you if the clients are happy. So client features we use are the client still or moving? What's the capability of the client? We know, for example, 7% of our 5 million clients under management don't have a 5 gig radio, and they're not going to grow one unless they upgrade. So the RF capability is very important, because if you set a 2.4 gigahertz power at 2 dBm, you may lose a bunch of devices. That's 7%, the bottom 7%. You want to know what applications they're using and what load they're offering to the network. So all these are Wi-Fi environmental features. What do we control? RF configuration parameters. And there's probably like 100 of them. And most people tweak 3 or 4 of them, but there's a lot more that people don't want to touch. But things that the people remember are the 20, 40, 80, whether you turn on DFS or not, what's the maximum power per band, what's the minimum probe threshold to get into an AP, what are transfer rates, beacon rates. These are things that we could control. And these are things that we are given. And then we basically build this model based on, we have close to 200,000 APs. The average time we've had in our database is probably 9 months. We have tens of billions of inputs and outputs to build this random forest regressor. You'll think, OK, 100 billion should be enough to know every single permutation of these parameters. It turns out that even 100 billion rows is not enough, in part because people are not brave enough to change the configs too much. So a lot of configs are repeats. So we will get much better once we are closing and driving the network. So we could actually change some of these parameters and explore spaces that nobody's ever tried. And then we could actually, this model will get much, much better. But in any case, once this model is built based on those 200,000 APs and 5 million clients, we throw in a new building. Somebody just joins our trial, has been in around for a week. We featurize the APs, we featurize the clients, and then we figure out, based on all the other buildings and APs and clients that are in our database that are similar, what's the best vector of configs that works for them? And that way we could optimize capacity, we could optimize application. Right now, we don't optimize anything on the jitter latency, but that's in the pipeline. So basically, we could come up with a building floor and figure out that, okay, based on the RF environment, these need one config and these need another config because it's open space ballroom and these are little offices. Okay, and these are actually real world. This is an example. This is actually just a screenshot from our dashboard for a specific one of our, it's in the top 10 that was in the very first slide. So it turns out that they thought that the dorms have a certain behavior and propagation. They said the power was very low, like 3 dBm in one band and 90 dBm in the other one, thinking, hey, I have AP every other room, we should make it. Well, guess what? Half the clients were on 2.4. Most likely the ones that were one wall away with 3 dBm kind of didn't do the job for them. They didn't know the construction materials of the building. And basically, this is before, this is after 2.45. So they're doing about half a terabyte each one of these bands. We have hundreds of cases like this. This is just one screenshot. And after they made the config change that we suggested, it dropped to about 20% in 2.4 and 80% in 5 gigahertz. And it's very hard to get above 90% because 7% are 2.4 only devices. So 90% is pretty much as high as you could get for the statistic. And yes, we've had pretty much half of our POCs or customers have at least 10 buildings like this. Another behavior is the DFS channels. I would say half of our POCs and customers don't have DFS on. This is a histogram of utilization versus channel. And you can see in this case, 2.4 is very loaded, the red. 5 gigahertz is pretty unloaded. DFS is all off. And this happens, half our customers look just like this. And what happens? They're afraid of radar events. They're afraid that devices don't handle DFS. So guess what? As soon as we light up our customers, we could quickly check the MAC addresses within hours, go into our database of 5 million device analytics, do some OUI clustering and MAC distances, and figure out what percentage of the devices in that building are not DFS capable, will not work if this thing gets turned on. And it turns out it's 2%. Ouch. So roughly 2% of devices are the reason people do this. They basically turn off the whole DFS band, and they're losing 2/3 of the capacity. So what's the point in getting 11AX, 80 megahertz APs if you're only going to have 2 channels? We've seen the deployments with actually 80 here and 80 here, 2 channels. Not very good. So in any case, we give visibility into the DFS events. So we also find anomaly detectors on some campuses that have more DFS events than others. Some are firmware-dependent DFS events, and some are real DFS events. Given that we have correlation across our whole database, we know if those DFS events are real or they're just self-inflicted by the chipsets that are looking for the radar events. And there's a lot of those. Those actually dominate. So this is another use case. This is actually real. This was actually very strange. We didn't even have a config knob to optimize for this because we didn't think it would happen. But basically, if you're following the colors, I don't know if you realize, these colors is lighter, slow speed, darker, faster speed. The legends is here. It's going between like 11B speeds up to 11AC speeds. And you can see this one's very faint. Like, why would this happen? They have they had wave 1 or wave 2 APs, and most of the data is being exchanged below 54 megabits. We did not have a knob for this. We weren't even checking for this. But when you do deltas across tenants, we find out that, hey, this one tenant, their speed distribution looks off. They actually turned off 11N and they turned off 11AC on these wave 2 APs. There's a knob for that. But somehow somebody they only did it for the guest network. So I think somebody figured out that if we turn off 11N and 11AC for the guest network, guests will use up less bandwidth. Well, guess what? They use more airtime. Yeah. They're probably not going to slow. If they're going to do a 3 megabits video stream, they're still going to do 3 megabits. They're just going to use up 20% of your air. So they thought maybe this was a rate throttling system. We told them about it. They're like, well, we didn't do that. I was like, OK. In any case, we'll add this to a list of things they have to monitor, which is you could turn off 11AC and 11N with a bit somewhere. And somebody might have just done it for testing. But in any case, this is real. This actually happened in one of the ones in the list. This is another thing that tends to happen in almost every place we go. We light it up. Within a week, we find that some APs have more than the maximum number of clients they can handle. The reason this happens is because APs that happen to be in bleedy buildings, if they're close to corners, they could get enough outdoor users to get the AP to the max in terms of maximum number of users, and then it doesn't take anybody in. So you could be inside the building right under the AP, and outside people got there before that, and the AP is host. So what we did for this is we have a random forest classifier. It's actually a regressor that actually tells you the probability that somebody is inside the building and using the IP or outside the building and using the IP. And this is just a distribution of the two. This is University of Washington. The left side shows you the indoor classified users, and this shows the outdoor classified users. And as you can see, the indoor ones follow building patterns, and the outdoor users are all scattered. It's a density plot. So this actually has multiple uses. One is, for a specific AP that's overused, you could go and figure out, okay, how many of the users in that AP were outdoor types or indoor types? And then you could put in policies. For example, set the probe threshold automatically so that it only takes the people inside the building. So if you set the threshold to 0 dBs, everybody could get in with 3 dBs. But if you set at 15, most likely most people inside it. But in any case, we could tell you how to set the probe threshold so that it only takes indoor users. Of course, you could drop the transmit power, or you could put outdoor APs. This is actually something that we see increasing in our tenants. They want to add more outdoor APs. And we have...
Go ahead.
Keep going. OK. So this is actually some details in the random forest regressor and how it classifies what's the probability of being outside for every single minute user. So in a campus like UW, 70,000 concurrent users, 8 hours, you can multiply it out, but there's like 100 million points in there. So every one of those 100 million points, we have to say, are you inside, outside? And then we could actually, OK, sorry, I mixed up. This is the model building, and that's the actual model application. The model building, these are the features that we use in a random forest algorithm, which is basically, of course, the SNR of the environment is not, when we're trying to decide whether you're inside or outside the building, is not a function of the AP you're connected to. It's actually a bigger function of all the other APs that hear you. Because, and actually it's intuitive, but this algorithm actually found it. And actually the #1 feature to determine whether you're inside or outside a building is actually the SNR of the APs you're not connected to. The SNR you're connected to this is the feature importance for the link of the AP you're actually connected to. These are all the other APs that hear you. It's actually more important. And there's things like distance, delta X, Y, Z, whether you're moving or not, and how long you've been connected. These are all features that you throw in there as categoricals, and then it figures out how important each one of these features are to decide whether you're inside or outside. This algorithm is showing 95% accuracy in the test set. And in addition to be able to help APs that every tenant has, some APs that actually get whacked, it helps us solve this problem. This is University of Washington again. You can see the contour of some of the buildings. And because we know every minute if you're inside the building, outside the building, we could get all the outside minutes, see if people are happy, applications, SNR, whatever you want to call it, and put some metric of this outside place deserves an outdoor AP. And this is just a contour it has 2 dimensions projected here. One is how many users, and the other one is how happy they are. And the purple is basically sea level. And then you can see it rising based on importance. And here, for example, is a very busy area. And actually, people that know this campus know this is right, because the dorms are here, the classrooms are here, and people walk along some of these corridors to get from their classrooms to their class, from their dorms to their classes. And actually, the orange squares are the locations where they actually have outdoor APs. But basically, we're telling them if you want more outdoor coverage, you have to basically put outdoor APs along this line. You have to put outdoor APs on this line. And these are the places you should put outdoor APs so that you have less people trying to get onto indoor APs. Because all these stations that we detected, they were connecting to indoor APs. Otherwise, they would not make this plot. This is another thing that's actually related to, I guess, what Anu was talking about. So it's not only the AX APs that need a certain amount of power to function at full functionality. The Wave 2 APs also had a similar thing, where they would need AT power, but some tenants did not upgrade the switch network, and they had AF powered. And this actually, we have some tenants where 80% of the APs are AP335s, and they're AF powered, and they're operating in the default mode, which is really, really low, 11N-ish like. So what we do is based on, again, we build models on station behavior, on what modes, performance versus number of antennas, and we could dynamically enable the AP to do more things. So the default mode they operated is very safe. Actually, you could kind of guess it by looking at this chain. So when the 335 AP gets AF power, it turns off a lot of things. So, but that's only because that's worst case thermals, user, CPU, all that stuff. But most APs are not working at worst case conditions all the time. So we could basically prioritize a number of steps of disabling antennas in 5 gig and 2 gigahertz based on your device capability. And actually, we have this running in a campus with 10,000 APs, of which 7,000 are in this state, where the APs double their capacity because of this thing. We study the environment, we got a configuration list, and turn on this mode, which adaptively turns down the AP as a function of the power it receives and how many uses it has. Okay, this is one of those that it'll be very hard to find if you knew nothing. It's kind of one of those needle in a haystack type problems. And this one actually has a cascade of like 3 machine learning algorithms back to back. The first one is time series analysis anomaly detector. Then from these anomaly detectors, we generate events. For a campus of this size, most of these campuses have 3,000 to 15,000 APs. They generate 20 or 30,000 anomalous events. You definitely don't want to look for those. I mean, you could have a humongous thing and just sort and filter and histogram and do some unions of things and try to find out something interesting. But what we do is we get all those events and then we cluster them. And these clusters are based on are the APs near each other on the same channel, of course on the same band, what the AP model is, all these stats. And then we go in this 8-dimensional space where we get these 20 to 30,000 anomaly events, and we find interesting correlations between them. And this one is a fun one. Basically, we found in one campus that they had a mesh network, each one in a star configuration with 4, they're actually here. There are 4 mesh points connected to one star. Each one of them is connected to a camera, and actually, when you go through a mesh, you have to double every packet to get through the mesh. Okay, oh my God.
That's okay, keep going.
So basically what happened here is, okay. So we basically have effectively like 8 cameras connected to one channel. And basically they were saying, oh, I can't believe you found this. That's why the cameras were stopping. So they basically had a 20 megahertz channel and effectively 8 cameras on that 20 megahertz channel. And it wasn't working. So we basically, our dashboard figured out based on clustering all those time series of anomalies, and it found a cluster of APs that are misbehaving. And we still didn't know that there was a camera connected to this, well, 4 cameras. But in case this was enough information for them to figure out, okay, yeah, sure, we'll go turn on 40 megahertz, and that should be okay for 8 cameras.
You know, one thing that I think we want to talk about was the device analytics. I think Jose talked about a lot of config recommendations, peer comparison, and we can make recommendations, right? And some of the recommendations involve that, hey, turn on DFS, right? And there was a question that people actually ask us that, hey, can I safely turn this on? Are there going to be actually issues with any of our devices? So here's some of our device analytics. So what we have is that we have actually in excess of 5 million devices from our trials that are actually in our database, where we actually have information about these devices in the context of whether they are, can they operate on both the bands? Can they operate on all, sub-bands within 5 gigahertz? So can they operate in Uni 1 band? Can they operate in Uni 3 band? We have all that information about that. We also have information about, can they operate at different beacon rates? There are some, anecdotal people come back and say, hey, Nintendos don't operate at like anything more than 2 Mbps. I have to have my beacon on for 2 Mbps all the time. And then we have actually data to prove that there are certain older versions of Nintendo that actually do that. But the newer versions of Nintendo are actually support all of that. So we actually did it for one of the clients where they had 100,000 devices on the campus, and it turned out that there were 78 Nintendos that were actually identified as having issues. And out of the 78, only 11 were really active on the network. Now, for that, with that type of data and with that type of information, they could easily make a decision to kind of, make changes in their network. So, the device analytics is at a larger scale is that, we have actually a lot of information, including K, V, R capabilities for these devices. And the key thing about it is the predictive analysis, right? So if you go into a new campus, before you learn about that specific behavior, a specific network, what you can do is that we have some partial MAC classification where you're looking at OUI, or certain times it's actually 30-bit or 32 bits in the MAC address that can actually classify a particular class of device, and then we can actually predict even though we have not seen that particular device. So for example, if you go into a new campus and it's actually predominantly connecting to 2.4, you might actually learn just based on observed behavior that it's not doing anything 5 gigahertz. But if you have seen that device class operate in 5 gigahertz somewhere else in some other campus, you can make a prediction that this device is going to be all right with 5 gigahertz. It's just that current RF configuration could be some that it's actually kind of preferring to connect to 2.4 gigahertz. So some of that predictive analysis is also built into this. I'll get into some of these are more of connectivity related issues. So this is a classic example where we actually found that there are some Cisco VoIP phones that were actually having very high DHCP renewals. And you can see here that basically this is a 30-day trend. It's pretty much happening all the time for each of these Cisco devices. And you can see this over 30 days, it has made like 500,000 DHCP renewals. So on an average, like 10 to 15,000 renewals a day, and with an average interval of 5-6 seconds, right? So now we have learned about this device. Now, if we see this device anywhere else in any of our tenants, we are actually able to highlight that more predictively before the issue happens. This is actually just showcasing that what type of capabilities. So this is what is our device explorer view. I just put my device in here, but it will have actually ability to show what type of capabilities the device supports. And I think what you're not seeing here is that we'll actually also have a stuff where DFS will be in red, where we'll know that this device is DFS incapable. We actually have conclusively proven that this device does not operate in a DFS channel. So and we found that in one auto-driven car manufacturing nearby here, they had actually some devices on the factory line that were actually DFS averse, and they would not. So it would be disastrous in that kind of environment to go and disable the DFS.
Is this a table lookup or calculation or a correlation?
It is a lot of pre-processing, and at this point, it's only a table lookup. This is one other example. This is again the example specifically I've gotten is from another tenant, but we found this at one of our tenants where a particular device actually was flooding the DHCP server and actually brought down the DHCP server for about 40 minutes. And it turns out that actually there are devices that actually do this spike. So you can see this. This basically 420,000 messages are actually sent by that particular device in 27 minutes to DHCP server. And one of the maximum duration is like continuous flood of over 32 seconds. So it's almost like a denial of service. Now these are actually not necessarily always a malicious devices. These are just malfunctioning devices. But having visibility into this. Again, this goes into our learning. I think I'll skip. I think mostly this is like you can, yeah. Any questions? Yeah. Go ahead.
I find that a lot of people like to turn up the configuration, like high transmit power, widest channels. Can you utilize that data and say, okay, we have these devices connecting and they do not perform well on a 80 megahertz channel or a 40 megahertz channel using this certain minimum data rate? Maybe a recommendation to ratchet down those settings?
That's actually an interesting question.
Yeah.
So now the device capability, in our current device capability, we're not keeping track if it's 80 megahertz or 40 megahertz happy. That's another thing we should add. Right now we have basically beacons and MCSs and 11 kVR, DFS, not DFS, but whether they're allergic to 80 megahertz, meaning they prefer or they have a bad performance at 80. By the way, I could tell you, 99% of the APs under management are on 40 or 20. Almost nobody has 80.
Yeah, like in the case of the Nintendos, I'm sure they're not using 80 megahertz.
Yes.
Completely.
11N cannot do 80, first of all. But if 11AC, you should be able to do 80. But we don't have that. But we should add it. In any case, we're not going to learn a lot about 80 because there's not a lot in our infrastructure right now. But as we start doing these reinforcement learning type techniques where we'll push 80 in some places just to see how it's doing, we'll learn whether devices have issues with 80. But right now, it's about half 20, half 40, and like 1% 80.
Yeah. Okay. All right.
Always good. All right, good afternoon. Vishwesh and I are here fully aware of the fact that it's just us standing between you and cocktail hour, so we'll make this as efficient as possible, which actually was designed to be a metaphor for security because security always seems to be in front of everyone else in the good things.